So the RICE project, which is called the Roosevelt Island Climate Evolution Project, or its acronym RICE, is a climate study. And what we're doing is we're using a record of the past by analyzing ice to understand better the climate behavior under changing conditions that we expect for the future. So one of the big concerns that we have is the stability of West Antarctica. West Antarctica holds the equivalent of about 6 to 7 meters of sea level rise. And should West Antarctica collapse, we would see over a certain time period that water contributing to the global oceans and rise sea level. What the RICE project is trying to achieve is determining how quickly this could happen and how quickly and how much water could be contributed to global sea level. So the Ross Ice Shelf is this largest ice shelf in the world. It has the size of France. And it sits just adjacent to West Antarctica because it's fed by West Antarctica. And so a large proportion of West Antarctica drains into the Ross Ice Shelf and from there into the ocean. Roosevelt Island is covered by ice. It's accumulated locally there. The Ross Ice Shelf flows around it, but it's completely covered under snow and ice. It's quite a large island. It's about 150 kilometers long and it's about 60 kilometers wide. And you just see it as an ever so gentle white hump in the middle of nowhere. And as you land, you suddenly feel rather small because it is just white all around you, white in the horizon, white and flat. One of the aspects that make Roosevelt Island such a good place to study ice cores is that there's a lot of snowfall. So the weather at Roosevelt Island can be quite changeable. You can have one moment beautiful sunny days, all you see is a white horizon with a blue sky on top of you. And within hours, you can find yourself, actually within minutes, you can find yourself in thick fog where you only find the next tent by following a flag line that we put between all tents. So we have about 30 tons of equipment that we bring onto Roosevelt Island. Many flights are necessary for this. These planes have skis to land on, and they land on a skiway. Once they land, each plane is met by a crew, and that crew will help to offload the plane. We use sledges and skidoos to move the equipment around. So everything is lined out, flags are being put into place, and we're creating long rows of equipment so that we can find it up a big snowstorm, food and fuel and other things to support us for a 4-month stay there. To be able to continue to drill throughout storms and other weather conditions, we have a drill tent that was specifically designed by Alex and Darcy, our 2 engineers. So this drill tent is 27 meters long, and it is our home for the entire time period for the drilling operations. The drill tent itself is only about 2 meters high, and to accommodate the drill activity underneath it, we have to cut a 4-meter deep trench underneath the tent. So we're using chainsaws to outline the area of the drill trench and then cut 4 meters down. Then the drill is set up, the core processing accessories are being set up. And then directly in the place where we're drilling, we also need to cut a further 5 meters into the ice, so a total of 9 meters, where the drill mast will swing up and down during the drill operation. So our drill was built by Darcy and Alex. It is based on a long proven Danish design that was given to us by our Danish colleagues. And then they used some modifications to adjust it for the particular conditions that we expected at Roosevelt Island. So the particular achievement of this drilling system is that we got extremely good core quality throughout the entire drilling process. So the drill is called an electromechanical drill, and what it means really, it is 3 knives at a round disc that are spinning around. And it's a little bit like your hand drill when you drill a hole into the wall. But instead of just making a hole, our drill cuts a ring and leaves the piece in the middle, the core, intact. Each time we send the drill down, the drill goes down on a wire. It cuts another 2 meters into the ice and leaves the middle bit, the core inside intact. We then break the core and bring the core up on a winch all the way to the surface again. When the drill comes to the surface, the mast goes from vertical and lays horizontal. Now we can extract the inner barrel that contains the core, and then the core is being pushed out onto the processing table. So when it is on the table, the drillers hand over the core now to the core processing team. The core processing team fits the core that just has been brought up to the previous piece, and these normally fit perfectly together, and then cut them into 1 meter length pieces. These 1 meter length pieces are now being packed into ice core boxes. These need to be kept at below minus 18 degrees during the entire time period. During the summer, we often experience temperatures that can be as warm as -5 or warmer even for some hours during the day. And so we have the storage cave, which is located 4 meters below the surface, where we store all the cores. So the drilling occurred over 2 field seasons in Antarctica. Both of these field seasons took 4 months. During the second field season, we drilled from 130 meter depth to the bottom, which was at 764 meters, drilling 20 hours a day. So it's very important that these cores stay below minus 18 degrees temperature to maintain the integrity of the records that we are hoping to get from the ice. And so the ice needs to be kept cold at site, but then also during transport. And then even once they're in the plane switches off all heatings and flies higher than usual. It flies at 10,000 feet to allow for colder temperatures inside the plane. The ice then is stored at Scott Base until the ship arrives and starts its journey back to New Zealand. Here we are at the New Zealand National Ice Core Research Facility at GEO-Science. The ice has arrived, and our international collaborators are here with us to process and analyze the core. So each meter is taken from the storage freezer into our work freezer. Here we cut the core using a horizontal saw, and this provides a good surface that is being cleaned to measure the electric conductivity. This is a first glimpse of the age of the ice. It provides a signal for volcanic eruptions and large climatic transitions. Then we cut now pieces for various analysis, and one of these pieces is now being transferred into the ultra clean lab here. So we take each meter of core and we place it on the continuous melter. This continuous melter is an ultra clean surface. It is a copper melter which is gold coated. And as the ice melts through the melter, we're dividing the material into ice that came from the interior of the core and thus has never been touched or handled in any way, is completely pristine, and the outer section that has experienced the cut in the bandsaws and has been handled by people. From this clean inner part of the core, we then can measure a variety of analyses. So the analysis can be distinguished into 3 groups. We measure the gases, we measure the water, and we measure the particulates in the ice. So here you see the water coming off the melter and is being pumped through these tubes to one of the critical points in the melter system, and it's called the debubbler. So you see this nice triangle. The water and the bubbles that are coming from the ice are being pumped into this triangle. The bubbles over to the gas analyzer, a laser that measures methane concentration in real time, while the water follows gravity and flows downwards and is being pumped away into many lines. One of the lines carries on 2 vials, while the other lines are going to 7 other instruments to analyze this water directly for the content of black carbon, dust, conductivity, pH, water isotopes, and calcium. By the end of the processing campaign, we will have filled over 100,000 vials. Each will be analyzed and will contribute to our understanding of the climate behavior in the past. Each of these drops of water is so precious to us because it contributes vital information on how Antarctica will respond in a warming world. This is important because Antarctica's response has the potential to fundamentally alter global sea levels, which matters to everybody.